Do you know why airplanes have their wings angled backwards like this? Today, I'll teach you why by using pen and paper. Let's go! Why are airplane wings swept backwards? When air passes over an airfoil, the cross-section of a wing, the unique shape of the airfoil causes the airflow to accelerate over the upper surface. Even if the airplane itself is flying at subsonic speeds, the geometry of the wing can lead to a local acceleration of the airflow, which may exceed the speed of sound in certain regions. As the air accelerates over the curved upper surface of the airfoil, its velocity increases and its pressure drops. This acceleration can sometimes push the local airflow velocity past Mach 1, the speed of sound, especially near the thickest part of the wing. When this happens, a shockwave forms. A shockwave is a sudden and drastic change in the properties of the airflow, including pressure, temperature, and density. It occurs when air transitions from supersonic to subsonic speeds in a very short distance. These waves cause a sharp increase in drag known as wave drag and potential destabilization of the aircraft as the airflow separation behind the shockwave reduces the lift. So how do we control the shockwave? We have to look for a specific Mach number called critical Mach number, which is the lowest Mach number at which the airflow over some part of the wing reaches Mach 1. Behind this point, shockwaves begin to form, leading to an increase in drag and a loss of efficiency, of course. The critical Mach number is specific to the shape of the wing and can be expressed as the ratio between the velocity and the speed of sound. For straight wings, or rectangular wings, the critical Mach number is relatively low, meaning shockwaves form at lower flight speeds. Swept wings, however, address this limitation by altering how the airflow interacts with the wing. So, swept wings reduce the effective Mach number experienced by the wing by changing the angle at which the airflow meets the wing. The airflow can be decomposed into two components: a perpendicular component, which affects lift and drag, that we called Mach 2D, and a parallel component, which does not affect lift or drag, and we call it Mach parallel. This reduction means that the flow over the 2D section of the wing is slower compared to the free stream velocity. In other words, the critical Mach number for a swept wing is effectively higher than that of a straight wing. This means, even if the plane is flying at a certain speed, the wing feels a lower velocity. Let's make an example and compare a straight wing and a swept wing with a sweep angle. Let's assume a critical Mach number for a straight wing about 0.5 and a 30-degree angle for the swept wing. If we recall the equation before, we will have a 2D Mach for the swept wing, which is around 0.61. So the critical Mach number is reduced due to the effect of the sweep angle. If you want to apply this concept in the opposite direction, you can say that the sweep angle allows the plane to go faster before encountering the same critical Mach number of a rectangular wing. As a result, the sweep wings allows for higher flight speeds while delaying the onset of wave drag and maintaining efficiency.